Sorry, that's very slow. But I think we are live, although I expected some problems. Anyway, I would like to welcome everyone again on this Tuesday seminar series at the Warsaw University Astronomical Observatory. Yes, we are now live on YouTube. I'm very glad to see this working. Today's speaker is Tomek Bulik, who's going to tell us about the very recent, just freshly published results on, sorry, it's talking me too much. Sorry, too many voices. So Tomek is going to tell us about new results from LIGO and Virgo collaborations. Tomek.
Okay, so I hope you can hear me. And I'm, as Łukasz said, I'm going to tell you about the new results from LIGO and Virgo collaboration. And as you all know, LIGO and Virgo have been working for quite a while and gathering data and detecting relativistic objects in the universe. LIGO, these are these two detectors on the left. The top is LIGO in Hanford in Washington State in the US. The bottom left is the LIGO in Louisiana, in Livingston, Louisiana. And on the right-hand side, we see Virgo, a 3-kilometer detector near Pisa in Italy. The principle of the detection is known. Gravitational wave passing through these causes stretching and squeezing of the space, and by measuring the difference of the effective length in the two arms, we measure the amplitude of the passing gravitational wave. So what were the observational runs so far that we went through? These are the O1 and O2 with their sensitivities, and we have also completed the O3 run, which was nearly 1 year of data that finished in April this year. So this run was quite successful, and in here you can see the duty cycle of the entire O3 run. So the yellow part of the pie is the triple coincident time. Nearly half of the time we had 3 detectors working. Then we have the, in green and red, we have the double time. And then this corresponds to single time. And just 3% of the time there was no detectors working during the O3 run, which shows for quite a good on time and good effectiveness of these detectors. Now here we see the Virgo sensitivity during O3. It has been improving all the time, and we started with the so-called BNS range below 50 megaparsecs, and then we ended with the BNS range of the order of 60 megaparsecs, and you see that the noise level in the detector was gradually coming down during the entire run. So the last week brought the first comprehensive part of publications of the results from these runs. So there were 4 papers published. I'll talk about 3 of them. The first of them is the Compact Binary Coalescence Catalog, GWTC2. Then there is the Astrophysical or Population Properties of Compact Objects from the second LIGO Virgo Gravitational Wave Transient Catalog. And then there are some tests of relativity, and I'll mention just a few of them. So there's quite a lot to talk about. So if you look at the entire O3 run, this is the timeline, and the vertical bars show different candidate detections that were published and that were made that people could follow, which were just candidates at the time and not confirmed detections. And people could, we published the locations in the sky and what characteristics of the object that should be. So there are potential BNS mergers, BBH mergers, and other unidentified phenomena. Out of this, so this whole O3 run has been divided into two parts. One is O38, another is O3b to the right. So today I'm going to talk about the results from O3a. So this left part of the diagram that is presented here, and so until a commissioning break that took part in October 2019. At that time, all the detectors were switched off for a month in order to do some engineering improvements, and then continued until the runs were stopped before the planned time because of the COVID pandemic. So this is the general picture of the black hole masses after the publication of this catalog, and it's getting denser and denser. We have now quite a plethora of black holes. Some of these binaries have already been published as interesting and individual objects before. We have now two binary neutron star mergers, and we also have one mixed merger that is here, and one black hole with an unknown companion merger that was also published before the catalog. But anyway, this picture is getting denser and denser, and now the detection of a binary black hole is rather ordinary, nothing unusual, unless it happens to have some very special properties. So what are the masses of the objects that we detected? So here we have the 39 new detections in the plane spanned by the total mass in the rest frame. So not as it measured by the detector, but in the the actual mass of the source. And on the vertical axis, we have the mass ratio of the binary. The dotted lines correspond to the left one corresponds to M1 equal 3 solar masses, where M1 is the more massive companion of the binary, and the right one that is shown here corresponds to M2, the lower mass, equal to 3 solar masses. So binaries in this left region are the potential binary neutron stars. Binaries to the right of this region are binaries where the two components had masses above 3 solar masses. So these are binary black holes. And this is the intermediate region where we had this two objects, 1904-26 and 1908-14, which come somewhere in between. And I will talk a little bit more about them in a moment. So when we talk about the compact object masses, we have this mass spectrum, and we have the neutron stars, which with the masses from 1 to 2, maybe to 2.5 or so solar masses. Then we believe that there might be a mass gap between the highest mass of a neutron star and the lowest mass of a black hole, which is approximately 5 solar masses. Then then we have black holes between 5 and 60 or so solar masses, and then we expect to have a second mass gap. So we do not expect stellar evolution originating black holes above 60 solar masses or so. Okay, so here's a slide with a few Polish things. Apologies for that. So That's the first object that kind of falls in between. There is GW 190421 with the total mass of 3.4, but the main component M1 can reach up to 2.6 solar masses. So it can stretch into the lower mass gap. Then we have 190814, which is either a binary black hole or a black hole neutron star. So this is an extreme mass ratio system with one component of the mass of 23 solar masses and another of 2.6. And the 2.6 solar masses is either a very massive neutron star or it's a very light black hole. We don't know. We haven't seen any electromagnetic signature after that. And we haven't seen the ring down of the newly formed object to be able to, or any to have a clear cut distinction between the second component, the less massive component being a neutron star or a black hole. But at least we know that there is something with this mass, which is relatively well constrained between, say, 2.4 and 2.7, maybe 2.78 solar masses. So this is an interesting object to consider. And then there is this behemoth that appeared and that was published only recently, which is GW 190521, which is this heavy case, which steps on the upper or second black hole mass gap, where the component masses are somewhere around 80 solar masses and 70 solar masses, which raises the questions about what is the origin, the existence of the upper or the second mass gap, and the question about the origin of the heavy black holes, whether this system originated in stellar evolution or it's a product of multiple mergers of stars, for example, in dense stellar objects like in globular clusters or centers of galaxies. So at least we know that there are some objects that tend to feel or step into the regions that we thought were off limits for compact objects like the first mass gap and the second mass gap. Now we can start the analysis of this data, like statistical analysis of the data, by thinking what should be the mass distribution of the black hole mass component. So in order to model the mass distribution, you have to assume something and then fit it and then decide whether it makes sense for such a fit, whether this is a good fit, which fit is better. Just we have just several measurements, and we have to guess how to model that. So in these papers, we assumed several mass distribution models. One is just a simple power law with sharp cutoffs. That's the model on the left. Then we have a broken power law with a smooth turn-on power law plus a Gaussian peak, which may mean that there is some specific mass where black holes pile up. And then the multi-peak model. So these models were used, and we fitted the data with those models. And here are the proposed models with their uncertainties. And the point is here that if you compare these fits and compare the quality of this of the modeling with these fits, the simple power law model is disfavored. This model really predicts too many high mass mergers that we do not see. Then the broken power law is looking much better, and there is some evidence, and I'll talk about this in a moment, that there is a peak of that this model should be modified by some peak of masses around 40 solar masses, that there is a pileup of black holes with those masses. So to make things more into context, these are the sort of intrinsic rates or distributions. So they are not, these are the distributions that are before taking the observational selection effects into account. If we want to compare what should be observed within all of these models, we can look at the next slide. And here we see the predicted distributions of observed masses M1 in each of these models. So you see that this truncated power law predicts a factor of 3 to 4 too many black holes of the mass of 60 solar masses. And if we take into account other models like the broken power law, then it drops quicker. And then there is some evidence for the peak around 35 or so solar masses, but it's difficult to say whether this is a real peak or it's a fluctuation. I'll show you the numbers in a moment. So now the question is about the mass range of black holes, and this is a table from the paper where we first take all confident binary black hole events, but we exclude GW 190814. So the event with this 2.6 solar mass event. And then we can calculate the number of the range of masses that contain 98% of all the masses, all the black holes. So regardless of the model that we take, we have this bulk of black holes between say 6 solar masses and 60 solar masses, and very few events outside of this range. Of course, if we include GW 190814, then this moves to a lower number, because this number is essentially determined by the lowest mass that we take into account. Now, if we exclude GW 190521, the very heavy event that could have some influence on the top range, but this influence is pretty weak. So from this, we can conclude that the bulk of black holes that we see is in this range of 6 to 60 solar masses, and there is very few solar masses, stellar mass black holes in binaries, in coalescing binaries above that. Now, this can also be seen in these two graphs. The left graph shows the broken power law indices estimate for the broken power law model. So the lower mass power law is something below 2, like 1.5. And then the upper slope tends to be something like 5. And to be honest, if we look at this distribution that you see here, they can also be well approximated by an exponential decay, because there is a linear scale here, there is a logarithmic scale on the vertical axis, and this is nearly a straight line that can be modeled by a broken power law, but it can also be modeled by an exponential, and such an exponential distribution of masses is something that we obtain in the binary population synthesis. Then the right plot shows the fraction of events in the peak. In the model where we assume that there is a peak of the mass, we can model what fraction of the black holes should be in the peak. So how many, how strong is the evidence of the peak? So and surprisingly, this shows that the probability distribution of this parameter is not peaked at zero. It drops down very much when we go to lambda peak equal to 0, which points to the fact that there is some evidence, some strong evidence for the existence of a feature, or you can say line, in the black hole mass spectrum, and the fraction of the black holes in this line or in this peak is about 10%, with the masses of about 35 to 40 solar masses, which may be telling us something about the stellar evolution and how black holes form, and that because of the winds, they and before they collapse, they pile up at this in this range of masses. So if we sum up the mass information, we have most systems with mass below 45 solar masses, most systems with equal mass. If you remember the mass ratio distribution I have shown you, most of the systems have nearly equal, have the mass ratio close to unity, but there are two notable exceptions, this 1904-12 and 1908-14. And there is the evidence for the first mass gap, but there is this 1908-14, which sits in the mass gap. So we think that we believe that the mass gap, or the dearth of compact objects between, say, 2 and something and 5 solar masses exists, but it is not that it's completely empty. There are some objects, but very few, that can fill the gap. Then the second set of issues is are related with the studies of the spins of the black holes. And with gravitational waves, we can measure the effective spin, which is this quantity that I wrote here. So that if we have the angular momentum and the individual spins of each stars, so this is the mass-weighted average of the projection of the spins onto the direction of the angular orbital momentum. So this quantity can, is equal to unity if the two spins are aligned with the angular orbital momentum, and minus unity if they are anti-aligned, and something in between most of the time. So if we look at the measurements that we have, this is the chi effective as a function of the chirp mass of the measured binaries. And we see that in most cases, this is consistent with 0 within the error bars, but there are some notable systems which differ from that, like 1904-25, 1904-12 again, then this system, 1905-17. So if we we can do the modeling of the distribution of this effective spins and see what is their actual distribution. So if we look at the distribution of the spins that we, with some model that we observe, so this is the picture on the right-hand side. This is the effective spin, and this is the probability distribution, the probability density distribution of this. You see that this distribution is centered on the positive values, but it stretches quite far to the left and right. And these are the parameters of this fit. So the effective value, the mean effective of the spin is positive. It's like 0.07, and sigma, the width, is 0.15. So this has an important consequence for the origin of these binaries, because if they originate from evolution in globular clusters, we would expect that the distribution would be centered on 0 and the spins would be essentially random in all the directions. We also see that this distribution is not going beyond, say, minus 0.04 plus 0.5, which means that the values of the spins is not, that it's not very often that the spins are maximal. Typically, the spins are smaller than maximal, and I will get to that point in a second. So given such a distribution, we can model it and find what is the symmetric part and what is the asymmetric part of this distribution around here effective equal to 0. And you see this. So the symmetric fraction, which is the so we can, okay, say what is the fraction of the positive spins, what is the fraction of the negative spins, and the fraction of the negative spins is about 0.27 with big error bars. Most of the spins are positive. There is some fraction that can be attributed to be vanishing. So from this, we can say that we can model what is the fraction of objects that come from globular clusters, fraction of objects that possibly come from the isolated evolution. So we can model that all of the binaries that can be attributed to the symmetric part of the distribution around 0 are potentially from cluster evolution, and the rest is from the binary evolution. And we see that there is a this fraction is something between, the fraction of globular cluster objects is at least 0.25. Now the second parameter, spin parameter that we can measure is this effective precession spin, which is connected to the projection of the spins onto the plane of the orbit. And it's the maximum value of these two quantities. One is just the projection of the spin of the more massive object, and another is the projection of the spin of the less massive object, but weighted by a function of the mass ratio. So this precession spin modeling is here. We see that the precession is typically non-zero, so there is an indication for the spins being, some part of the spins being in the plane perpendicular to the angular orbital momentum, which means that the directions of the spins are not always aligned with the angular momentum. And that allows us also to model the magnitude of the spins of the black holes. So here we have the on the left-hand side the magnitude of the spins, which are centered on a value of about 0.18, and the spin tilts, that is the angle between the probability of the angle between the spin and the angular momentum. So there is a preference for them to be aligned with the angular momentum. And the left picture shows that typically the spins of these black holes are small, are of the order of 0.1, 0.2, maybe less than 0.4. This is kind of surprising because it is extremely easy to spin up a black hole when you make it. The moment of inertia of a black hole is very small, and the maximum rotation of a black hole is relatively small. If you have a collapsing star that has moderate angular momentum, moderate angular velocity, and it collapses, it is relatively easy. It seems that it should be relatively easy to make a maximally spinning black hole. And actually, in order to make such a slowly spinning black hole, you really have to slow it down. So this is something that tells us, this is a very important information that tells us about the formation of black holes and how the black holes, how the collapse of massive stars takes place. So what is the angular momentum transport in very massive stars? So spins are not aligned. There are systems with anti-aligned spins, and spins are small, which is something that we have to take into account and understand. Okay, so the next point is the merger rate. So how many things like that do happen? We have narrowed down the merger rates of binary black holes. So this number went down now to something around 24 mergers per gigaparsec cube per year, and it goes up if we include 1904, 08, 14, and include all the system with masses above 2 solar masses, then this rate goes to 58. Then for the binary neutron stars, the rate is now constrained to something like 320 per gigaparsec cube per year, which corresponds to a number of about 30 per million years per Milky Way like galaxy. So this we are narrowing these numbers down, and we haven't provided the BHNS rate yet because this potential BHNS is an object for which we are not very sure what the companion is. So it may be the BBH or maybe a BHNS, and there has been a rate estimate based on this one object, which is with huge error bars. Another thing about the rate is that now we can already investigate the redshift dependence on the rate. We can model the redshift dependence of the rate. If we include the redshift dependence in the form of 1 plus z to the power of k, then we can model this exponent k, assuming some models of the mass distribution, and the probability density peaks for the positive values of k. However, k equals 0, which is no dependence, is not excluded. And for the best fit model with k of about 1.5, we obtain the local merger rate of 19 per gigaparsec cube per year, and then the rate increases. However, even if it increases, it does increase slower than the star formation rate. So that is consistent with the idea that the merger rate follows the star formation rate with a long delay, and so sometimes later after the formation, we have to wait a couple of billion years for the merger to appear, which smoothes down the dependence with redshift. But so we expected that this should be increasing, and we do not expect it to increase as fast as the star formation rate. So this looks consistent with what we think about the mergers. So let me turn to the fundamental physics, to the general relativity. And you probably have seen these pictures a number of times. The merger follows in such a way we have in spiral, then merger and ring down. And the point is that you can estimate the mass and spin of the merger product of the black hole based on the in spiral phase. And you can also estimate it from the ring down phase independently. So there are these two estimates that should be consistent if the theory of gravity is consistent, if we understand how general relativity works. So these are the constraints on the masses, so fractional difference of the mass after the merger and based on the ring down and based on the in spiral and the spin of the black hole, final black hole based on the ring down and based on the in spiral. And these are the combined constraints on these differences, and they nicely center on zero, which means that gravitation, that GR works, and we do not find any deviation from general relativity as yet. The second test that I wanted to talk about is the gravitational wave dispersion relation, which could be related to existence of a massive graviton, massive particle that carries gravity, and if in such a case the dispersion relation, so the relation between the energy and the momentum of the gravitational wave, which implies the velocity of gravitational wave, would depend on the frequency of the gravitational wave. And we can parameterize this as by adding some term like this, where alpha is an index, and try to constrain the coefficient A for each alpha. And that's done here. For different values of alpha, we see that this is still consistent with zero. So that tells us that we can place an upper bound on the mass of the graviton. This is this value, 1.76 times 10 to minus 3 EV over c squared, which is by a factor of 2 or 3 better than the best constraints on graviton mass from the dynamics of the solar system. So the conclusion here is that general relativity works, and there is many more tests described in the paper. In summary, we have lots of new data. We can constrain black hole masses distribution. We see the evidence for the existence of the first mass gap and some existence for the second mass gap. But this is an conditional evidence, because we also know that these gaps are not really void of black holes. We see black hole spins, and we know that black hole spins in these binaries are small, and that is something that is an important result for the astrophysics of massive stars. We now know the rates, and we can use the rates or rates ratios to constrain models. We can, of course, use all of this information to constrain models. We've done several GR tests, and O3b, the next catalog, will come in the near future. So in short, the gravitational astronomy is moving from a fuzzy picture like this to a real astronomy picture like that. And I'll stop with giving references to the 3 papers I talked about today. Thank you.
Okay, thank you, Tomek. I'll do the clapping. We can do reactions. There are claps here, clappings. Thank you. Right. If there are questions, then you can use the reaction button to raise your hand, and I will see it here, and I will ask you to unmute and ask the question. So please, we have time for some questions. I know it's difficult over Zoom, but I hope there will be some questions and some discussion. I will start. I will give some people some time. You have shown the histogram with different types of events discovered, and there was one which you said was marked as unidentified. So does it mean there is no template existing in the database? So it wasn't terrestrial. It wasn't any of known kind. Is there still some possibilities for something new which wasn't foreseen before, or can you tell more about this?
So this is so some signals are detected using templates, but we also have pipelines that look for signals for which we do not have templates. So we look for excess in signal to noise in coincident in detectors, which are coherent. So if we see something like that, then we have an evidence that we saw something that looks like a real astrophysical signal, but it's not modeled by any of the templates. So with this particular signal, since it is the right-hand side, we'll have to wait until the publication of O3b to find out exactly what it is, because I think it will be analyzed in gory details to get down to the bottom of it.
Okay, so when is the
because it may be that
plant?
When is the? I mean, this. I can give you dates, but I don't think that anybody really knows. I mean, the date for publication of this O3A catalog was moved a few times, so I can, sort of give you something like as soon as we can, which is, a few months, I believe, but who knows?
Okay, thank you. So questions, please. Everything was clear and obvious for everyone.
Okay.
Maybe there are some questions on YouTube. I will check. No questions. Okay. If there are no questions, then let's thank Tomek again. And we will have 2 more talks about gravitational waves coming, going into details on different aspects of gravitational waves. So thank you, Tomek, and I see you all next week. Thank you. Bye.
Okay, thanks. Bye-bye.
Goodbye. Thank you for your talk.